Okay, any questions to start off our Thursday lecture? All right. So what I'm going to do is I'm going to wrap up chapter 8. So we're just about done here. And just have a little bit to review over Lewis structures that do not obey the octet rule. And then finally, we're going to talk about bond enthalpy or bond energy. And that will wrap up the entire chapter. So we'll be done with the bonding chapter. Okay. So this will be the last week of my regular lectures. I'm going to be actually on the road driving throughout the weekend and into early of next week. So it may be difficult to get in touch with me over the weekend or Monday and probably even Tuesday. But by Wednesday, I should be stable. And so if you have any questions, you may need to wait a little bit to get a response. Okay. But I should be okay by Wednesday. So don't feel free to reach out. I just may not get back to you as quickly as I normally do. So let's talk a little bit about this idea of non-octet. We talked about it at the end of Wednesday's lecture. And really it comes down to just, several elements. We talked about in group 3A, how we have these two elements, boron and aluminum, and how it's not uncommon for them to be bonded to 3 elements. So for example, AlF3 and BH3. And when that happens, there just aren't enough valence electrons to get to the octet. So what you get are Lewis structures where you have 3 surrounding atoms, and the surrounding atoms follow their normal pattern of either an octet or, in the case of hydrogen, a duet. Okay, and so you end up with this sort of situation here where they have 6 electrons around the central atom. Okay, so this shows us that it is possible to have a structure, a molecular structure, where there's covalent bonding occurring, where the central atom does not have 8 electrons. So even though it's a great idea, this idea of the octet rule, it's a great rule for carbon, nitrogen, oxygen, and fluorine, there are some elements that will behave differently. And so we have to take that into account. So aluminum and boron, 6 valence electrons that can be observed. Then when we come over to the other side of the periodic table, not to the other side, but further over. Oops, be careful there. So we got group 4A, that has carbon, and it has silicon. They tend to obey the octet rule. There aren't it's hard to find any exceptions where they don't obey the octet rule. And then you get to group 5A, and group 5A is nitrogen. Again, it obeys the octet rule. I don't know of any examples where it doesn't. But the elements below it, phosphorus and arsenic, they do seem to have the ability to have more than 8 electrons in their valence shell. Okay, so this is what we would call an expanded octet. And we would claim that this is possible. Likewise, if you go over to group 6A, oxygen, again, octet, no exceptions really. And when I say no exceptions, I don't mean there are no exceptions. What I mean is we normally wouldn't consider those exceptions. Everything in nature is up for grabs for the most part. Sulfur and selenium, they do experience expanded octet as well. So where you're seeing this occur is in that 3rd row. So let me do 7A. And you get fluorine, chlorine, bromine, and I'm going to put iodine in here as well. And so you're really, it's all starting at the third row for this expanded octet. So I'm actually going to draw arrows here because it's all of these columns. And then you can even in groups, in group 8A, you can get expanded octet. But here it seems to begin with krypton. Krypton and xenon. Okay, so this is the expanded octet where it's a possibility. It doesn't mean that there's necessarily going to be expanded octet, but normally it can happen. But there's certain rules for this. So one is that these elements have to be the central atom. So they're not, it's not going to happen to any of these elements if they're not the central atom. Okay, so if you have, you know, S, 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 something like that, this is not going to have expanded octet. It's going to be octet rule. Same thing with this one over here. But the one in the center, it has the capacity for expanded octet. And there's all sorts of arguments about that. I'm not going to go through the details of that. So what you just need to remember is that if you have a formula with one of those elements, like phosphorus, and it's the central atom, if it has more than 4 surrounding atoms, it's got to be expanded octet. Right, it just has to be because it's got 1 bond to each surrounding atom. So that adds up to 10 electrons right there. Likewise, if you have a sulfur and it has more than 4 surrounding atoms. So here's sulfur, has more than 4 surrounding atoms. That's got to be expanded octet. Okay, it just has to be. Okay. Now, let's talk about some slightly different substances, these ions. And I'm going to show you 2 of them just for comparison. So this is called the phosphate ion. Phosphate is an important ion biologically. It's an ion that's found in the bone material. And this is the sulfate ion. I'll go ahead and call them ions. Each of these exhibits what we call expanded octet. So what I'm going to do for each of them is I'm going to show you 2 Lewis structures. One with the octet and one with the expanded octet. Okay, so in that structure, every oxygen has 3 lone pairs. And then there are 8 electrons around the phosphorus. That if the octet rule were holding for the phosphate ion, that's what we would expect the structure to be. But there is evidence that in fact, the structure is a little different. That what in fact happens is there's a double bond in here. And I'm going to ignore the issue of resonance here. There's also resonance, but we don't need to worry about that right here. So all I've done is I've taken one of the oxygen atoms, the one on the right, and I've pushed a pair of electrons to form a second bond to the phosphorus. So now the phosphorus has 10 electrons, right, instead of 8. So that's what we would call expanded octet. And what I'm going to claim is that, in fact, the structure of phosphate is a combination of both. There is resonance occurring, but that this is the dominant structure. There's evidence for that I won't go through right now. So really the question then is, how would we know that? How would we know that this is the dominant structure of phosphate as opposed to the one that's on the top. And the traditional way of explaining that is through something called formal charge. So if you have, one of those elements that I boxed off in the previous slide, phosphorus, sulfur, chlorine, bromine, iodine, xenon, and it's surrounded by oxygen atoms. What you want to do is you want to immediately say, oh, it's surrounded by oxygen atoms. It's one of those elements. It could have expanded octet. And then you can apply formal charge to test it. And here's how you do the formal charge. Just take the central atom. And the central atom in this case is phosphorus, right? Count up how many valence electrons it has. Now, phosphorus is in group 5A, so it has 5 valence electrons, right? Okay. Then what you do is you consider the octet. So take your octet structure and you do what's called a formal charge calculation. So what you do is you take your valence electrons, which is 5, and you subtract the number of bonds. Okay, so I'm going to take 5 and I'm going to subtract 4. And notice you get 1. We would call this the formal charge on the phosphorus. If that is not equal to 0, push 1 pair over to give it another bond. So look what happens. If I push this pair over to give another bond, now your formal charge would be equal to 5 valence electrons minus the number of bonds, you get 0. So I'm going to write a little 0 here to indicate that the formal charge is 0 on that phosphorus. And I'm going to write a little +1 here in parentheses to indicate that the formal charge is +1 on that phosphorus. So do the octet. If you count it up and you find that the number of valence electrons minus the number of bonds is not 0, then push another pair over to give it an extra bond. And then if that gives you a formal charge of 0, then you're set. That means that it's going to be expanded octet. It's relatively simple, right? There's some more complicated structures out there, but I'm not going to consider those for now. So what that tells us is that there's 5 bonds in the phosphorus. And again, it didn't matter which pair of electrons we pushed over. We could have done any of the oxygens or any of the lone pairs. But the point is there's 5 bonds instead of 4. Okay? And then that should work pretty well. Now let's try the next one. Let's try sulfate. Okay, the sulfate ion has a sulfur in the middle and then 4 surrounding oxygens. Again, I'm not going through all the, well, you know what, with this one, let me go through all the individual steps like we've learned to do Lewis structures. Sulfur is in group 6A, so it has 6 valence electrons. Oxygen is also in group 6A, and so it has 6 electrons. There's 4 of them, 4 oxygens. And then there's a -2. So remember, when it's negative, you add the electrons. So that means you got 32 valence electrons, right? You subtract off the electrons you've already used. So we have 4 bonds. Remember, each bond is 2 electrons, so that's 8. So 32 minus 8 is 24 electrons left over. So then we distribute them as pairs around the surrounding atoms, getting the surrounding atoms up to 8, right? Including the bond. Once you've used all 24, you stop. Now, if I had, let's say I had 26 electrons, I just did 24 right there to give each oxygen 6. If I still had an extra pair, I would put it on the sulfur. That it turns out it worked out 24. So now we're down to 0. And then remember we do this. So just like the phosphate ion, you assume octet rule to begin with. Then you do your formal charge calculation on the central atom. So the sulfur has 4 bonds. It's in group 6A. So you take the number of valence electrons minus the number of bonds. 1 bond would be 1, a double bond would be 2. So that would be 6 valence electrons. Remember, it's in group 6A. That's where that 6 is coming from. And then the number of bonds is 4. So you get plus 2. So that means it has a formal charge of plus 2. This is not an exact meaning, but sometimes we interpret it as sort of meaning that the sulfur in this Lewis structure, it behaves as though it had a charge of plus 2, as if it were ionic. But these atoms are attracted to each other through covalent bonding. So the atom tends to be more stable if it has a formal charge of 0, as if it were sharing its electrons completely. That's not the best explanation for it, but the true explanation is very complex. So we'll just sort of think of it as, hey, it wants to be covalent, not ionic, because it's a nonmetal. So a formal charge of 0 is better. So the way we go to a formal charge of 0 is by adding extra bonds. Because remember, you're subtracting the number of bonds. So if that gets bigger, then the formal charge gets smaller. Hopefully that makes sense. So one pair, I'm just going to pick one from one oxygen. That's going to give it an extra bond, right? So if you give it an extra bond, you'd be subtracting 5. But if you give it another bond from another atom, and again, pick another atom, it doesn't matter which one. I'm going to pick the one on the opposite side, but I could have picked the one on the bottom or the one on the top. You generally don't want to pick the same atom because then it would have a triple bond. So I'm going to pick another pair over there. That's going to form another bond. So now what are you going to have? You're going to have a double bond on the left and a double bond on the right, and then single bonds up and down. Okay, so now we're only going to have 2 lone pairs here. Oops, not there. And you're going to have 3 lone pairs here. And then that's -2. So now let's do the formal charge calculation on the sulfur. Sulfur has 6 valence electrons. It now has 6 bonds. So it has a formal charge of 0. So by having 6 bonds, it's as if the sulfur now is purely covalent compound, right? Or purely covalent elements. It's sharing enough electrons with oxygen atoms that it's no longer has a charge. It no longer is acting as if it were ionic, okay? So there you go. That again, these are both expanded octet. So really what I've given you is 2 categories where expanded octet occurs. The first one, so this is for expanded octet. The first one is where you have more than 4 surrounding atoms on the central atom, right? So SF6, PCl5, if you have more than 4 surrounding atoms, you're going to have expanded octet. The second category are the oxides, typically ions. So for example, IO4 minus. Okay, if you look at IO4 minus, 4 surrounding atoms, so maybe it's octet, but in fact, this one's expanded octet. And for that one, you use this argument. You draw the octet structure first, then you look at the formal charge of the central atom. And if the formal charge of the central atom is plus, then you add an extra bond to one of the surrounding oxygens. If it's +2, then you're probably going to have to draw 2 bonds from the surrounding atoms, 2 extra bonds to give 2 double bonds. No triples, just double bonds, okay? And there you go. So there's your expanded octet. So those are really, I would argue, those are probably, you know, all of the different types of expanded octets or non-octet rule. The first was boron aluminum, which is 6 electrons because it only has 3 surrounding atoms. And then you have expanded octet. Let me save this. And the expanded octet is the structure. Oops, let's go back to here. The expanded octet is where one of these elements is the central atom, right? So it's got to be the central atom. And either there's more than 4 surrounding atoms, or it's bonded to oxygen. And then if you do the bonding to oxygen, you check the formal charge of the central atom, and it's not 0. Okay, so these ones tend to want to have a 0 formal charge. Okay, so there you go. Any questions about non-octet? That's section, I believe it's 8.7. I think it's 8.7. It might be 8.8, but it's pretty much at the end of the chapter there.
No, Professor, but I have a question. On Alex, we have exercises. For example, like a student proposes the following Lewis structure for the neutronium ion. And then it's asking us to assign a formal charge to each atom. And we have left, central, and N, for example.
So you want to give me a an actual ion or molecule? Do you have one in handy that you want to look at?
Yeah. Just 1 second. It's NO2 plus.
Oh, NO2 plus.
Mm-hmm.
Oh, wow. Okay. And they want to do formal charge?
Yes, for each.
For each atom. Okay.
Mm-hmm.
So let me, if we're going to do each atom, let me add one more thing. So when you're doing the formal charge, you take the number of valence electrons. Remember, that's the number that comes from where it is in the periodic table, right? Group 5A, group 4A, group 6A. Subtract the number of bonds to that atom, just like I said. But in some structures, so for example, NO2 plus, you may need to do one more step, which is then you subtract lone pair electrons. And I'm going to point out when you subtract lone pair electrons, a lone pair has 2. There's 2 electrons in a lone pair. Okay. So you're just going to do one more step, which is subtract one more number. So let's take a look at NO2 plus. So the student proposed the structure. So I assume the student put the oxygens on the side as surrounding atoms. Now, what else did the student propose? Did they propose any double bonds or anything?
Just 1 second, I'll find exact. It was a triple bond on the left.
Cool. And then one lone pair on the oxygen here?
Mm-hmm.
And then the nitrogen didn't have any, just bonds, no lone pairs.
No, that's how it looks.
And then the oxygen is a single bond over here. Were there any lone pairs on that oxygen?
Only one.
Oh, only one lone pair. Okay. So I would argue here that we can do formal charge calculations. We'll do that. But there's another problem here. And the problem is that oxygen is very far from 8 electrons. So that's the primary problem with this Lewis structure. Oh, by the way, bracket plus, right? And so whenever I see a Lewis structure and I see one of these elements, particularly the surrounding elements and particularly second row elements, and I see an atom that is nowhere near 8 electrons. So like if you told me it's NO2 plus, so maybe the oxygen has 7 electrons.
Oh, I'm sorry, Professor. N was on the right side, O was in the middle, and another O on the left side.
Oh, okay. That could, okay, let's change that.
Yeah.
That could be better. So it was N, O, O, like that, right?
Mm-hmm. Yeah.
Which is, that's got other problems. And then there was a triple bond over here.
Between O, yes. Mhm.
Okay, and then so now there was only one lone pair here.
Yes, and 3,
And then 3 lone pairs over here?
yes.
Okay. Now that is interesting. Now that's intriguing. Typically when you have one atom of an element like nitrogen and 2 atoms of another element, usually the one where you have 2 are the surrounding atoms. But there are, sometimes it does happen. So let's take a look at this. So first thing I'm going to do is in fact, let me run this through you. This is sort of how I would look at things. 1, check the number of electrons. So if you're given a structure and you're asked to evaluate it, right? Is this a good structure? Is this a bad structure? Check the number of electrons first, because the biggest error that anyone, whether it be a problem or an actual person doing this, the first error that people make is they just do their accounting wrong. They don't add up the right number of electrons. So let's check it out. Nitrogen is in group 5A, so it has 5 valence electrons. Oxygen is in group 6A, so it has 6 electrons, 6 valence electrons. And then it's a plus. So remember, when it's a plus, you got to lose an electron, not gain one, but lose one. The plus means you're missing an electron, so you subtract it. So really what you get then is 16 electrons, right? It would be 12 plus 5 is 17, but you're subtracting 1, so it's 16. So let's make sure there's 16. 2, 4, 6, 8, 10, 12, 14. Oh, good. So the first step is good, 16 electrons. So that's promising. That looks pretty good right there. So then our next step is check the octet rule. And the reason we want to check the octet rule is that, if you take a look at the periodic table, second row elements, carbon, nitrogen, oxygen, fluorine, they obey the octet rule without exception. So you want to make sure that they're obeying the octet rule. So here's what you do. You take the nitrogen. The nitrogen has 8 electrons around it, right? Remember, you count all the bonding electrons and you count the lone pairs, so that's 8. The nitrogen in the center also has 8. And the oxygen at the right side also has 8 because it has 3 bonds and a lone pair. That's 8 electrons. So check 8 each atom. That's good. So far, so good. Now the third step you would do is you would check formal charges. And when you check formal charges, you want to be close to 0. Now, here's a little commentary about formal charge. When you're doing every atom in the structure, if you add all the formal charges, it should be equal to the charge of the ion. And the charge of the ion is +1. So if we do formal charges, they should all add up to +1. And they probably will, but we'll take a look and see. So let's go through it. We're going to do each atom separately. Let's do the nitrogen first. What you do is you take the number of valence electrons. Nitrogen's in group 5A, so that's 5. Then you subtract the number of bonds, 1. Right? The nitrogen only has 1 bond. It's a single bond to an oxygen. Then you subtract lone pair electrons. And remember, a lone pair has 2. So if you have 3 lone pairs, that's 6. Right? That's 6 electrons, 3 times 2. So what do you get? You get 5 minus 1 is 4. Minus 6, 4 minus 6 is minus 2. So I'm going to write up here minus 2. Now that immediately tells me we have a problem, because in general, you want formal charges to be closest to 0. Sometimes they can't all be 0. In fact, they can't all be 0 here because the whole thing adds up to +1. But you want them close to 0. So if you see a minus 2 in your Lewis structure, that's a problem right there. If the question were identify any problems with this Lewis structure, I would say, hey, the formal charges are out of whack. But let's do the central oxygen. Oxygen is in group 6A, so it has 6 valence electrons. It doesn't have any lone pairs, but it has 4 bonds, 1 on one side and 3 on the other. So 4 bonds, and then no lone pairs. So I'm just going to subtract 0 there. You get +2. Okay, that's a problem right there. That's a big problem. Okay. Formal charges that are nowhere near 0, meaning +2 or -2, that tells you that it's probably not a valid Lewis structure. And then you got the oxygen on the right side. So I'll write the surrounding oxygen. Again, group 6A, so 6 minus, this one also has 3 bonds, it's a triple bond. And then it also has a lone pair, so 1 times 2. Remember, the lone pair is 2. So what is that? 6 minus 3 is 3, 3 minus 2 is 1, so it's +1. So that, I would claim, for reason 3, is a poor Lewis structure. Okay. Now, in that question, what are they specifically asking you? They're asking you to calculate the formal charge for each atom.
Yeah,
Are they then ask you to evaluate it?
They're asking to assign a formal charge to each atom.
And that's it?
Mm-hmm.
Oh, okay. So they're not asking you to evaluate it.
So that's basically what we needed to, we needed just those 3 numbers.
So there you go. +2, I'm sorry, -2, +2, and +1.
Mm-hmm.
And to be honest with you, it probably is closer to this. This is probably what NO2 plus is. It's probably, you know, let's see. You got how many? 16 electrons?
Mm-hmm.
So it's probably, this is probably closer to what it is. Did I get 16? 2, 4, 6, 8, 10, 12. Oh, I got too many electrons, right? So that's a problem right there. So let me get rid of that pair. Make that a double bond. Is that reasonable? 2, 4, 6, 8, 10, 12. So I got 16 electrons. Each one has 8 electrons, right? The nitrogen has 8 because it has 4 bonds. The oxygens each have 8 because they have 2 bonds and 2 lone pairs. And then if you do your formal charge, let me do formal charge because that's really your question. The oxygen on the left here has 6 valence electrons, so 6. It has a double bond, so you subtract 2. And then it has 2 lone pairs, but remember, each lone pair has 2 electrons. So this is going to give you 0. That's better. So our third category here, that you want to check the formal, they should be close to 0. That's a good sign right there. Now we do the nitrogen. The nitrogen is group 5A, so 5. It has 4 bonds. That's kind of cool, 4 bonds. And then you subtract no lone pairs because it doesn't have any. So you get +1. And then the oxygen on the right, it's just like the oxygen on the left, exactly the same. 2 bonds, 2 lone pairs, it's the same element. So this one's 0. All the formal charges add up to +1, so that's good. So even though that question didn't ask you that, what we've done, what I just did right there was I showed that this is probably what the structure is. The one that the student gave you, NO2 plus, was probably a bad structure because the formal charges are nowhere near 0, whereas in this structure, they're pretty close to 0, okay? But that's how you do it. That's how you do it. So you take the number of valence electrons from the column, group 1A, 2A, 3A, 4A, 5A, 6A, subtract the number of bonds in the structure, and then subtract the number of lone pairs, but remember each lone pair is 2, so you subtract 2 for every lone pair. So if you had this, here's oxygen, for example. So there's your oxygen atom. Oxygen's in group 6A, so 6. It has 1 bond, so you subtract 1. It has 3 lone pairs, so 3 times 2, and that's going to give you 0. So you would say it has a formal charge of 0. Okay?
Thank you. I was confused because nitrogen was not in the middle. That's why I was a little...
Yeah, that was intriguing. But, you know, that's very common. So like what happens is if I were giving a written test like we would do sometimes, and I said, hey, here it is, NO2 plus, write the Lewis structure. Probably about 10 to 15% of people, you know, 1 out of 10 or 2 out of 20 would do this. They would put the nitrogen on the left. They say, oh, NO2, so NOO. But what we find is that in nature, it is more common when you have a formula like that. The pattern is the one where there's only one of them tends to go in the center, and then the other ones surround it. Kind of like a tree, right? Like if you think about it, the structure of a tree is typically not a trunk and then a branch and then a branch. It's typically a trunk and then a branch and then a branch, right? There's something to that, I suspect, that has to do with just how things grow in nature, how they attach to each other, right? There's more stability when you have something in the center and then think, you know, like that's how we're built, right? Like we don't have an arm attached to another arm, right? It just doesn't make sense to have something built that way. So I think it's the same thing here.
Thank you.
Okay, so the last issue that I want to talk about here, let me save this one, are the bond enthalpies. Now, I love the bond enthalpy topic because they're very easy calculations. And then I think Alex, actually, they call it bond energies, which is fine. I think that's actually technically more correct to call them energies than to call them enthalpies, because enthalpy suggests heat, right? If you remember the term enthalpy, what we would say is that if we're at constant pressure, Q sub P, meaning the pressure is constant, the heat is equal to this delta H, which we call the enthalpy. It's really the enthalpy change, but we call it enthalpy for short. And then in fact, we said, hey, we can even call it heat for short, right? So bond energy is probably the more correct term, but textbooks often will call them enthalpies. So what I'm going to do is I'm going to show you how to calculate or how to use bond enthalpies, bond heat, bond energies, to calculate the energy of a reaction. So remember, when we're talking about chemical reactions, there's two aspects of a chemical reaction that we generally consider. One is the transformation of matter, meaning that atoms rearrange themselves at the molecular level. So for example, if I take H2 and I react it with O2 to form H2O, really what we're saying is, hey, these atoms, these hydrogen atoms, there's 4 of them here, right? 2H2 means there's four hydrogen atoms. Really what's happening is they're transforming into new substances, but it's really just a rearrangement of atoms, right? So what's happening is these, 2 of these atoms are moving, the hydrogen atoms are moving over to the oxygen and attaching to it so that you get this oxygen molecule getting converted into water, right? Oop, I don't need to do that. So there's a water molecule, right? And then these other hydrogen atoms are just attaching to this oxygen to give us another water molecule. It's kind of cool. So that's one aspect of a chemical reaction, is this transformation of matter from one substance into another. But again, it's at the atomic level, and we still have oxygen and hydrogen atoms. We're not saying that anything's really changing. They're just rearranging their positions, right? And so, that's one aspect. But the other aspect is heat, right? The other aspect is energy. So what happens is when you do these reactions, many of them, the reactants have a certain amount of energy, right? So I'm going to write an energy level diagram. I'm going to claim that these reactants, the H2 and the O2, they have a certain amount of energy. Like things have energy, right? Like if you have matter, you have energy. So the reactants have energy. And what we'll claim is that the products may have a different amount of energy. And if the products have less energy, right? So I'm going to write this line lower. So the water has less energy than the hydrogen and oxygen. And if that's true, and it turns out it is, then that energy has to go somewhere, right? So like if you're at the top of a mountain and you jump down to the bottom of the mountain, you have lost what we call potential energy. And that potential energy has to go somewhere. And really where it goes is you are moving fast once you jump down, right? It's getting converted into kinetic energy. So you're just moving faster. Same thing happens in a reaction. That energy's got to go somewhere. And typically what it does is it leaves as heat. And remember, heat is the transfer of thermal energy to the surroundings. So if we were to take hydrogen and oxygen and burn the hydrogen and the oxygen to form water, what would happen is we would heat the air around it. It would get hot, okay? And that's what we call heat, is the transfer of really kinetic energy, right? Thermal energy is just the vibrations and the movement of these molecules. So some of that energy gets transferred to the surroundings, and those molecules are now moving faster. So what is it about a chemical reaction that causes this to happen? Why does water have less energy than hydrogen and oxygen? So why do we get energy coming out of it? And it turns out it's the chemical bonds. All of the energy changes that we talk about in a battery, in a combustion reaction, in metabolism, it's all about bond energy. Each chemical bond has a certain amount of energy. And if you end up with weaker bonds at the end than what you started off with, there will be a transfer of energy occurring. If you end up with stronger bonds in the products compared to the reactants, there will be a transfer of energy. So if the bond energies are different between reactants and products, there will be a transfer of energy occurring. Okay, so let's take a look at it. Now it turns out that there are, I'm not going to go through this because it's a long lecture, but it turns out there's ways to measure bond energies. We can measure bond energies. The way they're typically measured is by measuring how much energy it takes to break them. Okay, so what I'm going to do is I'm going to list out a few bond energies. So the first one is a carbon-carbon bond. How strong, how much energy is in that bond? And it's 347. And let me put the units in here, kilojoules per mole. Okay, those are the same energy units we used with enthalpy back in chapter 5. Okay, so we're using the same units. A carbon-hydrogen bond, 414. Now, when you look these up, you may see slightly different values. So for example, 414, you might find that it's 412 or 413 or 412. Just use what's in your ALEX table, okay? The textbook is pretty similar, but there are some slight differences. So just use the ALEX values. An oxygen-hydrogen bond, 460. An oxygen-oxygen double bond, 495. Let me do another one here. Let's do a C double bond O. 799. This one's really strong. 799. That's a big, strong bond there. Okay. I think that's it. I'll just put those ones up. But there are all kinds. You know, there's 100 different bonds you could look up. So these are the strengths of the bonds. We call them bond energy or bond enthalpy. We also call them strength of the bond. So what we would do is we would say, hey, that carbon-oxygen double bond is stronger than that oxygen-oxygen double bond. Stronger. Oh, by the way, an oxygen is very small. It's like 130. Very weak. That's a very weak bond. So, right, so this one's weak. This one's strong. Okay, that's some of the terminology we use. So really what we want to do then is we want to calculate the energy change. So I'm going to call it delta H. We want to calculate that for a reaction using these bond energies. So we look these up in a table and we use those values to figure out how much energy is going to be released in a reaction. Okay, so here's how you calculate it. Delta H for a reaction, RxN for reaction, is, I'm going to do a little math notation now, sigma, which is the sum. That means you're going to add up. You're going to add up the number of moles, N for moles, like PV equals nRT, of a product times the bond enthalpy. So I'll use BE for bond energy or bond enthalpy for that particular product. So you're going to add up all the bond enthalpies of the products and you're going to subtract the sum, again, adding up all the number of moles of the reactant times the bond enthalpy of each reactant. The reason it's a sum is because you could have more than one reactant and you could also have more than one product. So this is each reactant and this is each product. Now notice this is N. This is the coefficient in the balanced equation. Now, if they told you the actual number of moles, if they said, hey, you got 1.35 moles of this product, you would put in 1.35. But typically, they're just going to give you the balanced equation. And if you're given the balanced equation, just use the coefficient in the balanced equation. Okay. It's very rare. Well, I can't say it's rare. I have seen problems in textbooks where they say, hey, 1.55 moles of this reacts with 2.75 moles of that to form 3.62 moles of this and 3.62 moles of that. If that's the way it's working, then you can just put those numbers in. But you're more likely just to see a balanced equation. And if you just see a balanced equation, just use the coefficients in the equation. So let me show you an example. I'm going to do the combustion of methane. Okay, CH4 is methane. Methane is natural gas. It's the primary component of natural gas, okay, CH4. And it used to be that all methane was essentially just burned off into the atmosphere. When they would drill for oil, there would be methane and they would just build tubes and then just let it go into the atmosphere and try to burn it off the top. But it's now valuable. People use it for fuels. So it's now, they collect it, okay? So CH4, methane, natural gas, it will burn in oxygen, which is in the atmosphere. Combustion means you're going to form carbon dioxide and water. I'll put water in the liquid state. Okay. States of matter here. Actually, oh, I'm sorry. I'm going to put this as a gas. There's an assumption in all of these bond enthalpies is that they're all gas phase. That's sort of a weakness of this type of problem. We don't have bond enthalpies for liquids or solids. So we can only do it in the gas phase. So here's how you go about it. You're going to use this formula here. But how do you use that formula? You have to look up these bond enthalpies. So which bond enthalpies? Well, is there a carbon-carbon bond in there? There's no carbon-carbon in any of these molecules. But there is a carbon-hydrogen here. But how many? So here's what you do. You start by drawing the Lewis structure of each substance. By the way, I didn't balance it. I need to balance it. There we go. So there's a methane. Methane is CH4. Then you got two oxygens. So I'm going to put 2 And then you got oxygen. Oxygen is a double bond. That's the accepted Lewis structure for oxygen with 2 lone pairs on each. So notice I put a 2 there. That 2 is from the coefficient, so it's got to be balanced. Then you have carbon dioxide. Again, I'm just going to draw these Lewis structures. I'm not going to go through the effort of figuring them out because that takes too much time for now, but you'll have to do this yourself. Okay, so there's CO2. And then 2 waters. Again, there's 2 of them. And then water is HOH with 2 lone pairs on the oxygen. Okay, so make sure you know how many, the balanced equation, make sure you know how many of each of those molecules. Now what you're going to do is you're going to count up bonds. So what you're going to do is you're going to say, okay, are there any carbon-carbon bonds? There's no carbon-carbon bonds in there, but there is a carbon-hydrogen bond right there. I see it. And that's 414. So then you count up how many of those bonds there are. 1, 2, 3, 4. So then you say, okay, 4 times 414. Right? That's going to be the carbon-hydrogen bond. Then you go to the next reactant, O2, O double bond O. Oh, there it is, O double bond O. Now there's 1 O double bond O, but there's 2 of them. So 2. So 2 times 495. Okay, that's why that coefficient is important. So that what I'm doing is I'm using these coefficients there. So there's your 2 right there. Then you go to CO2. CO2 has a carbon-oxygen double bond. That's 799. But there's 2 of them, right? There's 2 of those bonds in there, so that's times 2. Okay. There's only 1 carbon dioxide, okay. Then you come over to the last one, there's OH. OH is 460. Now this is where you have to be careful. There's 1 bond there and there's a second there, so I'm going to multiply that by 2. But there's also a 2 here. So there's 2 of those bonds, so there's a 2 there, but there's 2 as a coefficient. So I'm going to multiply it by 2 twice. Okay, so 1, 2 is for the coefficient, and the other 2 is because there's 2 in the molecule, 2 of those bonds in the molecule. Okay, so really you're going to multiply it by 4. So now if you do this multiplication, you get 1656. 1656, right? 4 times 414. 2 times 495 is 990. 2 times 799 is 1598. And then 2 times 460 is 920. And then you multiply it by another 2. So that's 1840. Okay. So now I've done all of them. So look at what we had to do. We had to take the balanced equation, draw Lewis structure for every substance in there. Okay. So that's why we're not going to have you do like glucose. It's too big of a Lewis structure for you to do it in a manageable amount of time. So it'll be for simple molecules. And so you draw the Lewis structures, you figure out which bonds are in there, you look up the bond enthalpies or the bond energies from the table, and then the hardest part really is counting up how many to multiply together, right? So if you've got 4 of these, you got to multiply it by 4. If you've got only 1 double bond, there's only 1 in there, but there's 2 of the oxygens, so you got to multiply it by 2. Whereas here, there's 2 double bonds, so you got to multiply it by 2. Here, you got to multiply it by 2 twice, once because there's 2 of the bonds, but another 2 because there's 2 of the waters. Then you plug it into this formula. Okay, so I guess what I'm going to do is I'm going to get rid of these numbers here so that you can, I don't want to move over to another slide because then you won't see how these numbers are coming from, and I'll forget the numbers anyways. Okay, so what I'm going to do is I'm going to take products. Oops. It's reactants minus products, sorry. Typically when we do changes, we do products final minus initial, but there's a reason why we do reactants minus products here. P. The reason we do reactants minus products here is because of the way bond energies are measured. They're measured by breaking, but when we're doing the calculation, we're just using them all as break. We're using them all as breaking, but none of them is forming. So that switches reactants and products. So I'm sorry, for this one, when you're using the bond energies, do reactants minus products, okay? So let me go through this then. So we're gonna add up the reactants. So the reactants are, 1656 plus 990. So there's your reactants. So I've summed up the reactants. Now, what about that N? I already took the N into account. The N is the 1 there. So I have a 1 here. The N is the 2. I already took those into account by just doing those multiplications there. So just take the numbers you have, subtract the sum of the products, 1598 plus 1840. Okay, so reactants minus products. I'm sorry, I told you products minus reactants because typically it is reactants, products minus reactants, but for bond enthalpies, you want to use reactants minus products. So 1656 plus 990 is 2646. 1598 plus 1840 is 3438. So then you subtract those two. So 2646 minus 3438, and you get minus 792. Again, the units, even though I only put them in the table at the beginning, are kilojoules per mole. So there's your delta H. So what this, notice it's negative, right? So it's exothermic. That's consistent with what we know about combustion, right? Combustion should be exothermic. That means it's releasing energy. Here's why it's releasing energy. And this explains why things are endothermic or exothermic. What happened is we're taking the reactant energies, how strong the reactant bonds are, and we're subtracting how strong the product bonds are. So if you get a number that's negative, that means the products have a larger number, right? If you get negative, that means the first number is smaller and the second number is bigger, larger, greater. So that means that these are stronger bonds and that these ones are weaker bonds, right? That's how it would work. If these numbers, the sum of those numbers is larger than the sum of these numbers, you're going to get a negative number. So that tells us that when we get an exothermic reaction, that means the products have overall stronger bonds than the reactants. If you got a positive number, then that would be the opposite. That would mean that overall the reactants have stronger bonds than the products. Okay? And so that now explains at the chemical level, at the physical level, why some reactions are endothermic and other ones are exothermic. It just all has to do with which bonds are stronger. And so by having this table of bond enthalpies or bond energies, we can now make predictions about exothermic and endothermic reactions without actually having to do the heat reactions, you know, to measure the temperature change of water like we had to do back in chapter 5. Now we can just use these values and get our answer there, okay? So just a reminder, it's reactants minus products, and the reason for that is because of the way we measure bond enthalpies is how much it takes to break the bond, not how strong. You're measuring how strong it is by measuring how much energy it takes to break it. They're all going to be positive. So what we have to do is we have to do reactants minus products because of that, okay? The N is the coefficient. So that's the 2, the 1, and the 2. But you can circumvent even using that just by taking the balanced equation and counting up how many bonds total are in that Lewis structure. So here there's 1 for the oxygen, but then you multiply that by 2. Here there's 2 bonds, so you have a 2, but the coefficient is a 1, so you don't have to multiply by 2 a second time. But for the water, you got to multiply by 2 twice, once for the number of OH bonds, and then once for the coefficient. Then you just add up the reactant numbers, add up the product numbers, and then take reactants minus products, and you're set. You've got your bond enthalpy change for the reaction. Okay? Any questions on that one? Okay, that is the last topic from chapter 8. So we're done with chapter 8. And so good luck working on them. And again, reach out if you have any questions. And if I am a little slow getting back to you, don't fret about it. It's just because I'm on the road. But by middle of next week, I'll be back and be able to respond more quickly. Okay. So have a great day, you guys. Have a great weekend. Good luck kind of getting ready toward the end. So I know a lot of people are taking 2 classes. And so if you're taking 2 classes, good luck getting all that done in the next week and a half. But I'll talk to you later. Take care.
Thank you.
Thank you.
Bye-bye.